Hello everyone, welcome back. This is Professor Herring. In this video, I'm going to guide you through some extra practice problems dealing with intermolecular forces. These are going to touch on the vast majority of the learning objectives for this chapter. So let's begin. In this first set of questions, you're actually going to be asked to do two things. One is to determine which molecule has the highest boiling point, and the other is to determine which has the lowest boiling point. So I recommend that you pause the video, try this on your own first to determine both the highest and the lowest boiling points, and then I will walk you through the process. Welcome back. So in order to determine the boiling points, we need to remember that the boiling point will go up as the overall intermolecular forces goes up. And we need to evaluate for all types of intermolecular forces. In one of the last slides on the previous video, I mentioned how there are 4 considerations that you want to make. The first is to consider hydrogen bonding. Generally speaking, if a substance has hydrogen bonding and others do not, it's going to have higher intermolecular forces. After you consider for hydrogen bonding, you want to then look at molar mass. And if the differences in molar mass are greater than approximately 10 grams per mole, then that's probably significant enough to affect the boiling points. After you've considered molar mass, assuming that they are the same, at that point, you would want to evaluate for polarity. You want to check and see if molecules that have roughly the same molar mass are of different polarity. And the higher the polarity, the higher the intermolecular forces. The last point to consider is shape, or surface area. Remember that in order for molecules to interact, they need to have high contact area. So if you have a shape that's all scrunched up and small versus one that's elongated and more straight, then the scrunched up one is going to interact less with other molecules and therefore have a lower boiling point. So let's evaluate for each of these. None of these have any hydrogen bonding. Remember, hydrogen bonding, it requires that we have a hydrogen with a covalent bond to either nitrogen, oxygen, or fluorine. And that's going to interact with the lone pairs on a nitrogen, oxygen, or fluorine. Oops, let me give us some more room here. The lone pairs on either a nitrogen, oxygen, or fluorine which is polar. That nitrogen, oxygen, or fluorine must have a negative charge on it, otherwise this will not work. So none of these exhibit hydrogen bonding. Molar mass considerations. In that case, I'm going to erase this just a minute so we can see it. We see that we've got heavy and light molecules due to the difference in molar mass of the sulfur. Let's draw this here again. And that's our hydrogen bond. So again, we can look at these. Molecules A and B are equally heavy, and molecules C and D are equally light. And so all we need to do at this point is, well, first of all, we recognize that there's no real difference in polarity. The sulfur to carbon is going to have a slight bond dipole. So these two are going to be slightly more polar. But the more important factor is the molar mass differences. And since we know that this is heavy, it's also slightly more polar than these molecules, but compared to from A to B, it is extended. Molecule A is much more extended and has much higher surface area than B does, and therefore it's going to have the highest boiling point. And when we look at the lowest boiling point, we're looking for our lightest, most compact molecule in this case, and also it's exhibiting no differences in polarity, and that's going to make D be the lowest and A is the highest. Okay, let's try a different question. Which intermolecular force could form between C2H2 and PCl5? In order to know what kind of intermolecular forces are going to come into play, we want to identify what types of molecules or compounds these are. So, unless it's given to you, you need to draw out their Lewis structures. And then from that, we need to identify, do we have ions? Are these molecules polar? Or are they nonpolar and can only exhibit induced dipoles? So none of these are ions, and the way that we've identified that is because ions, we would see that they should have a charge, or possibly if you're having a metal bound to a non-metal. So neither of these are ions, therefore we cannot have any types of interactions involving ions. The molecule on the left is not polar, there are no polar bonds, whereas the molecule on the right is polar. We know that chlorine is more electronegative than phosphorus, and that's going to lead to some bond dipoles pointing out away from the phosphorus. Keeping in mind that in 3 dimensions, we really have something that looks more like the following. What we have is these bond dipoles that point out and down. From the phosphorus. Therefore, they cancel each other in the left and right directions, but nothing's pulling up to cancel them out going down. And that's going to give us a net dipole moment that is in the downward direction. In terms of induced dipole, every compound can have an induced dipole. In other words, all that this requires is electrons. If it has electrons, then you can induce a dipole, even if it was already polar, even if it was already an ion. And that's because what we're talking about is disrupting the electronic distribution. And anything that has electrons can be disrupted. So we have a polar molecule with a dipole, with a molecule that has no dipole. And in terms of determining what IMFs are present, all we do is base it on the identities. So a molecule with a dipole, with no net dipole, but can be induced, is a dipole-induced dipole interaction. But because they can both also be induced, we also have induced dipole interactions, also known as dispersion or London dispersion forces. So again, all we're doing is looking at the identity. The identity, we have a polar molecule that has a dipole and a nonpolar molecule that has no dipole. We also have a polar molecule that can be induced and a nonpolar molecule that can be induced. If you haven't noticed already, we're going to always have induced dipole forces. Let's move on to the next one. Put the following molecules in order of increasing boiling point. We've already looked at something similar, but in this case we want to rank them. So remember, increasing IMFs leads to increasing boiling point or melting point. Our first consideration is hydrogen bonding. And 3 can exhibit hydrogen bonding. It can interact with other identical molecules. There's a lone pair of electrons. This oxygen is negatively charged. This hydrogen is covalently bound to an oxygen, so we can have hydrogen bonding. There's no hydrogen bonding here, and that's because this hydrogen is actually bound to the carbon. The next thing is in terms of molar mass. But when you look at the molar masses of these, there's no significant difference in the molar masses. They're all less than 10 grams per mole different. The third is looking at polarity. 3 is polar as is 2. The last thing to consider is the shape. They all have the same relative shape, and so that's not going to affect anything. But because we can differentiate, we know that 3 is the highest because 3 has hydrogen bonds. And we can differentiate between 2 and 3 versus 1 because 1 is not polar, so the lowest must be 1. That's going to then get us 1 is less than 2 is less than 3. And that's it. And if you look at the actual boiling points, they match that. Let's take another look at a question here. Which pair of these molecules can form hydrogen bonds with each other? So in order to determine this, we need to evaluate whether we have hydrogen bond donors and acceptors. And a hydrogen bond donor, as we talked about, is where we have a hydrogen with a covalent bond to oxygen, nitrogen, or fluorine. That's going to make that bond very polar, and it's going to create a special type of dipole-dipole interaction called a hydrogen bond. In order to accept that donor, we have to have an acceptor, and that's where we have a partially negative oxygen, nitrogen, or fluorine with a lone pair. And so we really need, there's 3 criteria: hydrogen bound to NO or F, partially negative NO or F, and a lone pair. If we don't have all 3 of those criteria, we don't have the possibility of hydrogen bonding. So looking at pair number 1, we have a donor and an acceptor. In order to satisfy oxygen's octet, we're going to need 2 sets of lone pairs in this molecule. And it can donate because we have a hydrogen covalently bound to the oxygen. However, looking at nitrogen, we have no donor nor acceptor. You might think it's an acceptor because we have nitrogens with lone pairs, but it's not polar. We have to meet all 3 criteria in order for it to participate in hydrogen bonding. Try pair number 2 and see if you can figure that one out. Pause the video now and then come back after you've tried. Welcome back. So let's take a look. Pair A is an acceptor, or in pair A we have an acceptor, and that's because of the lone pairs, and that's a partially negative oxygen. However, we only have an acceptor here as well. Lone pairs on the oxygen. Remember, this is a carbon, and so this is not polar. Pause the video and try for pair number 3. In pair number 3, we also have an acceptor. This is identical to the molecule we just looked at above. And in this one we have a donor. And that's because we have a nitrogen covalently bound to hydrogen, and that can be donated, and it would look something like that. Now, this is not an acceptor. And that's because nitrogen has no lone pairs. So it can't accept a hydrogen from a different molecule. Okay, let's move on and take a look at some more hydrogen bonding. We want to know which of these could not have hydrogen bonding as part of its intermolecular forces. Again, we're applying the same strategy. Go ahead and pause the video, try this out on your own before I walk you through a solution. Welcome back. So I'm going to illustrate for you one way you can look at this in terms of a visual representation. If you look at oxalic acid, molecule B, and we draw multiple of it, it can interact through hydrogen bonding. We have on each molecule an acceptor and a donor. We have the acceptor because it's a partially negative oxygen and it has lone pairs. And the donor because we have a hydrogen covalently bound to a different oxygen. In C, H2O2, we can also have hydrogen bonding, similar to oxalic acid. Molecule D, it can have hydrogen bonding as well. The main difference here is that we're looking at nitrogens that are accepting and donating rather than oxygens. And then finally, methanol, E, can also have hydrogen bonding as one of its intermolecular forces. Acetone is the only of those molecules that cannot, and that's because it has an acceptor, those electrons, the lone pair electrons, but it has no donor. For our last question, I'd like you to pause the video and try this on your own. See if you can think through this before I give you the explanation. Welcome back. So if we're looking for which of the following is in order of increasing we want to place them in order of increasing intermolecular forces, we need to consider some things. First of all, we talked about how we have hydrogen bonding to consider, molar mass. Then we look at polarity and shape. So if we draw out these molecules with their skeletal structures, they look like the following. What we can see is that shape's not really going to matter. Nothing is similar. Okay? We do have their dipole moments, so we can compare the polarities. We have molar masses, so we can compare those. And then hydrogen bonding, it looks like we have two different molecules, both water and this fatty acid can participate in hydrogen bonding, and so that's going to be a little bit ambiguous, especially given the fact that they have competing trends for molar masses and their polarity. So if you take a look at the molar mass and rank them, then you would say that hydrogen has the lowest intermolecular forces, followed by sodium chloride, then the C2H-Cl2F3, that's a freon, and then the C18H36O2, which is a fatty acid. Okay? If we look, however, at the polarity, we're going to see a different trend. And how do you know at what point which factor is going to be most important? It turns out that if you're given the melting or boiling points, you always use those as your indicator of strength in terms of intermolecular forces. When you have drastically different molar masses or dipole moments, then it's impossible to tell from those data alone if you have competing trends. And so you must take a look at the melting point or boiling point data, or later when we look at viscosity or surface tension. The macroscopic properties melting point, boiling point, etc., those rule. Those are our ultimate indicators of the intermolecular forces. That's it for this video. Thanks for watching. If you have questions, ask on Piazza and office hours or recitation. Have a good day.